So my feed says that I have 11 people logged in so far, so I'm waiting on a few more people.
I have a quick question.
Mhm.
So I have done the math review,
Okay.
and now I haven't taken math since undergrad, and I finished in 2001, and chemistry since junior year of high school, which was longer ago. And anyway, I've done it, and I had to like kind of look things up because I couldn't recall it immediately. But do you have a recommendation for like a review like online that you're aware of that I could just go to like just further my review process a little bit? 'Cause I know how to do the math. It's just a matter of refreshing, some of the formulas and just doing it more, I guess.
For the purpose of math, the general online recommendation is Khan Academy.
Khan
Is
Academy.
Yeah, KHAN Academy.
Okay.
They have both a kind of like a testing system, but they also have kind of a tutoring system.
Okay.
I've known quite a number of people to use it. My daughter uses it for extra help with her algebra, um,
Great.
to provide more than one point of view when she's going through something.
Okay.
That
Okay.
might be
Cool.
the best I could suggest. That's easy
Okay.
and free.
Yeah. Yeah, I'm just looking for more review just because again it's been a while and it's some of it's coming back, but it's like I just would like to do more to make sure that I'm like, kind of sealing it in.
So yeah, I would say look up Khan Academy, and there's a whole bunch of different facets to it. They do more than just math,
Okay.
but there is a big segment that is math. I have mixed opinions about their chemistry, but their math is pretty solid.
Okay, cool. Great. Thank you so much. I appreciate it.
So I have 22 people who are registered on my roll. I have 16 people showing tonight so far. I changed where the Zoom link was. I dragged it from the bottom of the page all the way up to the top of the page to hopefully make it easier to find. If you are someone who was not around on Tuesday night, I did the recording and I posted it two ways because the first way I posted it, somebody sent me email saying it didn't really give you a link to the actual recording. It just gave you a link that claimed, oh, here's where the meeting was. And I wasn't sure what that problem was. So I went ahead and loaded it up to YouTube and then copy pasted the YouTube link. So you should have two different ways. Um, if you were not here on Tuesday, if you want to go back and have a look through that, I mean, it is roughly an hour and a half long. The first part of it is me waiting for some people to log on. And then a big chunk is about the syllabus. And then the actual chapter one stuff is probably about 45 minutes in would be my guess. So if you decide you want to go back and look at that, hopefully now it is actually viewable. All right, so we are going to pick up with screen share and keep on going in chapter one then. We did not cover a whole lot of the chapter on Tuesday. So let me find my... Not... Okay, I'm like having screen sharing problems. It's being flaky here. Oh, there's where they are. For some reason, it was way at the bottom of the page. Okay, so hopefully you should be able to, this is the file that is loaded to Canvas that is for chapter one notes. And the last thing we talked about on Tuesday was a little periodic table information. So that's kind of where we're going to pick up tonight, just to kind of backtrack just a smidge.
I think we were on reactants and products.
No, I know I didn't get that far.
I've got notes.
I'm pretty sure I left off with talking about the stuff on your periodic table. Anything above 100 and anything above 100 is probably not going to be useful. Being super familiar with the name that goes with the symbol is really a critical thing all the way through this semester and actually on into next semester too, because it never really actually goes away. All right, so elements and atoms. If you have an element, okay, you cannot break it down into a simpler substance, okay? And the reason it says under normal laboratory conditions, if you have a nice convenient nuclear accelerator, all bets are off, okay? Otherwise, if you break it down, then you end up with protons, neutrons, and electrons, which are not actually an element. The smallest bit of your element is an atom. So then we have another pairing that's really very similar. We've got compounds. So if you have a couple of different elements and they're all stuck together, this is how you get your compounds. One of the things that is true about the compounds is if you had the right type of reaction, you could actually split a compound back into its elements. Even water, okay? If you pass an electrical current through water, you can get the hydrogen gas and the oxygen gas that it was made from back from your water molecules. So same sort of comparison though. If you have a molecule, it is the smallest unit of a compound. One thing that's also true that's mentioned there is a molecule is neutral, okay? A molecule has no charge on it. Charges are something that we will get into greater depth later. Most of the things that are occurring in this chapter are either individual elements or just compounds that we're not really doing a lot with. We have to have a place to start. So if you're actually looking at compounds, and I just picked on a couple of the simplest ones there. Water, obviously, you've got 2 hydrogens and 1 oxygen. Now, one thing that you may or may not remember from high school level stuff is any element that you have just 1 atom of, they don't draw the number next to it. So like when you see the H2O, the 2 is both sort of to the right and slightly subscripted. So that tells you that you have 2 hydrogens and 1 oxygen. And then I gave you a glucose molecule, 6 carbons, 12 hydrogens and 6 oxygens. So same basic idea here. I had multiples of all of the atoms that are located in that molecule. So 6 carbons. You can tell that because of the subscripted 6. When we start talking about putting things together, okay, a mixture, and this is actually a topic that's going to come up in lab in a few weeks. This is one of the labs that we are actually doing physically. We are doing this for real and not just digitally. A mixture usually is a couple of things blended together. And we're gonna separate them out into heterogeneous and homogeneous. Excuse me. So if you have something that is not the same all the way through. This is Virginia. We are below the Mason-Dixon line. If you are familiar with the whole concept of the really gross and disgusting thing of take the can of fruit cocktail and dump it in the Jell-O and then shove it all in the fridge till it solidifies, which I think is just gross as hell, but it's a heterogeneous mixture because depending upon where you stick your spoon, you're not going to get the same thing all places in the bowl. On the other hand, okay, I'm sitting here, I'm drinking a Diet Coke. My Diet Coke is a homogeneous mixture. So, especially because I've only opened it, like 20 minutes ago, it has carbonation because the carbon dioxide is dissolved in the liquid. It has coloring, it has sweetener, it's a liquid. All of that is the same, basically all the way through the can. So, composition and properties are uniform. They're the same all the way through. Now, another word you could apply to my Diet Coke is the fact that it is also a solution. So people tend to think of solutions as solid dissolved in a liquid, which is true, okay? But you can have other things that actually qualify as solutions too. So whipped cream, squirt the can, or old school, actually whip it with a whisk and incorporate air into the liquid. It's actually a solution, gas in a liquid. Fog is the reverse. Fog is liquid in a gas. Egg white is technically a solution because it's a solid, albumin, dissolved in a liquid, which of course makes it that viscous, slippery stuff if you touch it. But it is actually—
Is that mayonnaise?
Mayonnaise is actually an emulsion.
Isn't that suspension
Um,
in a liquid?
Mayonnaise is an emulsion because the suspension is stabilized. Presuming that you made your mayonnaise correctly, if you stick it in the fridge overnight and you take it back out the next morning, if it's still mixed together, it's an emulsion. There is actually a very slight technical difference there.
Huh.
So one of the things that's true about the mixture is you can separate them. Now, the mixture that we are going to be doing in lab has sodium chloride, salt, silicon dioxide, sand, and then a slightly more exotic third component, which is called ammonium chloride. And we're going to use a set of different techniques to allow you to separate them all out and get their individual masses, which hopefully, fingers crossed, add up to the original mass of your sample, give or take about 1/10 of a gram, and give you a way to learn a series of techniques that are part of the separation idea there. All right, pure substances. Pure substances are a little bit less of a straightforward concept compared to elements versus compounds. So water is pure. Water is a pure substance, but it's a compound, not an element. Knowing that it has definite composition is kind of the key component there, because it doesn't matter whether the water was rain or came out of your faucet or you purified it from ocean water. Water itself is always 2 H's and 1 O's. Okay, so the fact that you can get it all the way down to a certain level of purity, and then if you break it any further, it's not water anymore. If it's H's separated from the O's, then it's not a pure substance. Then we've gotten back to actually separating it down into its individual elements. All right, one of the things I talked about on Tuesday was this chapter is very much a conglomeration of separate topics. So we're going to jump topics again. This one is about properties. Properties is something we actually use a lot of in lab. We probably use them way more in lab than we do in lecture. Physical properties, you don't change the identity of your substance. So if I have a piece of silicon, I can weigh it, I can observe a color, it has a texture, silicon is actually kind of shiny when it's pure. All of those things are things that don't make it not be silicon. So clarity, among other things, helps you sometimes determine how pure something is, okay? Things that are not clear, not see-through, are often made of more than one substance. And your tip-off is kind of their clarity issue there. One of the labs that I'm gonna end up giving you a bunch of pictures combined with videos, because this is one of the ones we're not doing in person, involves color. So you're going to end up seeing some pictures of a batch of different substances. Colors are a tip-off. Nickel is often green. Copper is often blue. Manganese is usually purple or black. Cobalt is usually pink. All of these things are sort of tip-offs that help you when you are actually dealing with substances in the laboratory situation. Odor, okay, if I hand you a beaker full of clear liquid and I ask you, do you think this is safe to drink? Odor might be a tip-off because water shouldn't smell. Rubbing alcohol is clear and liquid. You wouldn't want to drink that. Acetone is clear and liquid. Again, you wouldn't want to drink it. It also has a really characteristic odor because acetone is one of the things that's the main component of nail polish remover. Texture. Certain things tend to be smoother if they are more pure. The same thing is true of luster. Think about a brand spanking, okay, we'll say the word 2020, penny. It has that sort of pinky orange color. If you have a penny that is 10, 15 years old, and you've been, carrying it around in your pocket for 3 days, it has that sort of brownish color to it. Now, part of the reason is that the copper of the penny's surface has combined with not only the oxygen in the atmosphere, but the oils from your fingers and anything else that it has come in contact with. So luster's another tip-off about purity. Now, hardness is kind of more of a geology deal. If you take geology, one of the things that they teach you about is I think it's called the Mohs scale, that allows you to figure out how hard your rock is. Less true of chemistry, but geology is also chemistry, okay? Because rocks are made of compounds. Viscosity. I know that's a word that kind of most people, if you talk about viscosity, people think motor oil, because that's a word they always use in the ads. Viscosity is how thick something is, okay? If you have king syrup, which is a kind of syrup that some parts of the US use on pancakes. It is super, super thick and pours really slow. So
Molasses.
yeah, it's thick and not easily pourable. But on the other hand, gasoline's even less viscous than water. So viscosity can be a tip-off as to identity. Melting point and boiling point, there are gadgets that are available in labs that allow you to figure these things out. Now, the gadget that's used for finding out melting point, we don't actually have one of those. Somebody, okay, I gotta figure out how to click this. Somebody asked a question, and I'm trying to figure out how to. Why would it let me? Hang on a minute. So, Ian, do you have a question? Because I don't see a question.
Yes, ma'am. It's giving me a little blue hand after I raise my hand.
Okay.
So as far as hardness goes, I've got an example that I'm curious about. I was drilling into some stainless steel today, and given the rate at which I was drilling, I was told by my NDT inspector that if you get stainless too hot, it'll actually the metal itself will change its crystalline structure, and it'll actually form a small kind of diamond-like coating into the hole where you're drilling. So that's why you've got to drill at a certain rate very slowly. Would that be an example of a physical or a chemical property?
Because you are changing the compound with heat and friction, well, kind of the same thing. I would say that's a chemical property, because if you're actually changing it, then it's not strictly a physical then.
Okay.
Because stainless steel has carbon in it. Carbon and
Chromium.
yeah, I was going to say either chromium or manganese, depending upon exactly what kind of steel it is. You are probably changing its identity slightly. So that would not make it physical. That would make it chemical.
Okay.
Now, boiling point, we could do in the lab. It's not actually one of the things that we do this semester. Boiling point involves usage of a strangely shaped tube into which you put an upside down capillary tube. And it's actually a really simple thing to do. And you could find out what the boiling point of a pure liquid is by heating it with your Bunsen burner and watching it. When it suddenly stops bubbling and the water starts, or the liquid starts going backward up into the capillary tube, you've reached the boiling point. It's a really cool little deal. We are doing density though. Density is for the people who are in the, I think it's group A, who are doing lab on Monday. And everybody else will be doing it. The other section of lab will be doing it on the following week. We are doing density in lab. You are going to be doing densities of solids and liquids. So we are going to use pipettes for doing density of solids. Actually, I said that wrong. Density of liquids, and we're going to be using graduated cylinders to help us do volume for the solids. So you are actually going to get some real world practice on that. All right, a couple more words. These again are kind of a crossover into lab information. Something that changes depending upon whether, did I hand you a teaspoonful or did I hand you a bucketful? Okay, those are called extensive. Mass and volume are typical extensive properties. Intensive Doesn't change. I could give you 3 grams of paradichlorobenzene, and it would have a particular melting point. I could give you a kilogram of paradichlorobenzene, and it should have the same melting point. Okay, it's not dependent upon how much you've got. Now, kind of along with the physical properties, we've got physical changes, and this also kind of goes along with the idea of you are not allowed to change what it is. Freezing, melting, boiling, condensation, sublimation, deposition, which is actually something that's going to come up again when we do the separation of mixture lab. All of those are physical changes, but so is cutting, grinding, anything that leaves it what it is. So, okay, if you cut a log in half, okay, with your chainsaw, you haven't changed what it is, it's still wood, okay? Even the sawdust is still wood. It might look different, it's because it's kind of curly and powdery now, but it's still wood. On the other hand, if you set the wood on fire, that is not a physical change. That's a chemical change. Yes.
So
Ian.
again, that brings me back to so if the chemical properties are still the same, however, again, the arrangement of those atoms are changed into a different, like I said, crystalline structure. Wouldn't that be more of a physical property change as opposed to a chemical, even though you're using heat to rearrange the atoms to a different structure?
So we don't do crystal lattice structure stuff until second semester. But if you have altered locally the percentage of manganese or chromium or carbon that's in your iron, I still think that probably falls in the category of chemical because it's a localized thing. I don't really have that much familiarity with that, but that would sort of be my opinion based upon the way the definitional stuff works.
Okay.
So chemical properties and chemical changes are kind of almost the same thing. When we talk about chemical properties, the only difference there is we're calling it, okay, we're using the word ability. Ability meaning you might not have done it yet, okay? And I gave you gasoline as an example. So gasoline can burn. But if you have the little red plastic tank like you're going to fill up your lawnmower, okay, and you haven't actually done anything with it yet, it's still sitting there in the tank, it has the chemical property that it could burn and become primarily carbon dioxide and water once it's burned, but you haven't done it yet. Once you actually put it in the lawnmower, internal combustion engine and all of that, and you actually start turning it into the exhaust from your lawnmower, it then has undergone a chemical change. So they're almost the same thing, but not quite, okay? Think about the property version as we may not have done anything with it yet. The actual change usually implies that it either just happened or is in the process of happening. So we need to be able to write this stuff down, okay? We need to be able to write it eventually into equations. And equations in chemistry are a little bit different than equations in math. There's some similarities, but there's also differences too. To quote a really bad joke of, it's like math was fine till they decided there needed to be letters with numbers. It is sort of an old and evil joke. Anything you start with, the beginnings of your reaction, we're going to dub reactants. it is traditional to write them on the left-hand side of your arrow. Now, if you go in to take second semester, it's actually a little bit more complicated than that, but we're going to kind of stick to the basics for this semester. Whatever you made, the stuff you got when the reaction happened, these are your products. And the arrow itself, okay, when you're doing math, there's an equals. When you're doing chemistry, you can read it a bunch of different ways. Some textbooks will go, this yields this. Some of them will go, this gives this. Some of them will tell you reacts to form. Sometimes they will even be more specific and say synthesizes or decomposes or gases evolved or some other things like that. It's a way of telling you what happened. So if you have a chemical change going on, there are visual, and I use the word visual loosely, tips. We're gonna spend a moment here talking about the 4 different things that might happen. So, color change. Remember the penny? Okay, the penny from your pocket. There's the brand new penny, which is a sort of pinky orange color, and there's the old penny, which is that shade of brown, because it has copper oxide on the outside. Part of that was a result of the chemical change. Another thing is if you add iron, iron in a solution is yellow. Thiocyanate, that's a polyatomic ion we'll get back to later, is relatively clear, okay? The iron is pale yellow. You pour both of them together and you get a bright red-orange, obvious color. That's part of your tip-off that the reaction happened. Making solid. Some of the labs that we are dealing with this semester, okay, not the metathesis one, because that one you're going to see the videos and you're going to see the pictures. You don't get to do that one. I believe we are actually doing the limiting reactant one, which involves a precipitate. You're pouring 2 solutions together, and not only did it change color, it got cloudy. Sometimes so cloudy that if you let it sit there for a little while, it starts settling to the bottom. I have been told, I have not tried this, that if you pour Bailey's in Pepsi, you get a precipitate. If you're of legal age, you can try that and decide whether you think that's actually true or not. Formation of gas. Okay, I am old. I am really old. When I was a little kid, when you bought Captain Crunch, you got a plastic submarine in the box, okay? And the plastic submarine had a little hole in the top. And came with instructions that said, pack baking soda in the little hole and add a couple of drops of vinegar and then drop it in the bathtub. Well, because baking soda and vinegar generate carbon dioxide gas, your little plastic submarine would sort of dive and rise as it blew off the little bubbles in the bathtub. Also, chances are, depending upon where you go, where and when you went to school, you might have been subjected to the how to create a volcano in middle school, which is also baking soda and vinegar, and usually also food coloring. So you get gas. Carbon dioxide is gas. We are going to make carbon dioxide in one of our labs. Now, one of the reasons I said visual, maybe not exactly true. Things that might happen that produce heat, sometimes a flame, but you also have heat absorbed, okay? If you go skiing One of the things that many of the ski supply stores sell in the lodges at a lot of the resorts is hand warmers. And the hand warmers are often something that are operate a little bit like a siloom, that you put them in your hands and you like snap them and you shake them up and they get hot. Okay, not forever. They get hot for a couple of hours. Okay, this is also how MREs work. Okay, if you want to heat your MRE up, it has a basically it's kind of a little chemistry reaction going that allows you to either add water to the powder that's in the pouch, or some of them also have this kind of break and shake mechanism. If you buy a first aid kit these days, not the like $3 ones, the ones that are like, $15 or $20. Most of them will come with an ice pack that also is like, usually has instructions like place on firm surface and strike with fist. So you either hit it or break it and you shake it up and it gets cold, really cold. All of these are also tips of reactions. And I probably ought to go on YouTube and find the link, that the flame thing, that there is a couple of YouTube videos of people who deserve Darwin Awards. A couple of frat boys that somehow acquired a relatively large chunk of pure sodium. And they put a big galvanized steel bucket out on their front lawn, and they hurled the big chunk of sodium into the bucket, which has water in it, and it goes kablooey, okay, which also involves flame. So there are some fairly epic things that can happen in terms of just adding things together and stuff happens. All right, we're about to switch gears again. So a little bit more away from the reactions part, over to the math part. So if you have a measurement, it's got to have two parts. Okay, there's the number part, but there's also a unit. Okay, and depending upon if you've had physics or if you've had some other science classes, you may be familiar with scientific notation. Scientific notation is not exactly the same as exponential notation. It's a little bit narrower. So your number out in front is supposed to be between 1 and 10. Exponential notation is less rigorous. You just have a number out in front. It doesn't have to be between 1 and 10. But for scientific notation, we're kind of limiting it. And then you have an appropriate power of 10. So I gave you a really big number there. I gave you 4 million. You don't see where the decimal point is. The decimal point is over past the most right zero. If you moved the decimal point from all the way past that 6th zero, all the way up to where the first comma is, you would have 4 times 10 to the 6th. You have moved your decimal place 6 spaces. Specifically, it's a positive exponent because it's a big number. Big numbers written in scientific notation have positive exponents. What about the flip side? Here I gave you a little tiny number. Now, if I move the decimal on this one from where I can kind of see it all the way over there near the left-hand end, and I move it till it's between the 3 and the 4, I would have moved my decimal point 5 spaces, but in the opposite direction. So this one is a negative 5th power. Little tiny numbers written in scientific notation will have negative exponents. One of the things you need to be able to do, and this is one of the things that's covered in the homework set, is you need to be able to comfortably go back and forth between normal numbers and scientific notation. So now we're going to switch over to the units part for a little bit. So one of the things that's covered in your textbook is the SI system. Okay, so SI stands for Système International. The French invented it, they got to name it. In fact, the International Bureau of Weights and Measures is in Sèvres, France. It's basically the metric system, but there's a few differences. So let's scroll down here a little bit. Your length base unit is meter. Now here's one slight difference between regular metrics and SI. Note, it says mass is kilograms because gram is the base unit, but if you're talking about SI, they have declared that kilogram is the base unit. Time is seconds. Temperature is not Celsius. Temperature is Kelvin when we are talking about temperatures. Amount of substance, this is something that's going to come back to haunt you a great deal in a couple of chapters, is the mole. This semester, we're not going to be doing electrochem, but that's a facet toward the end of second semester. Amperes. Luminous intensity, basically how bright something is. It's called candelas. There's a whole bunch more. I just picked a few of the most common ones and added a couple of the less common ones there. Everything is in base 10. You should know the 5 standard prefixes. Yes, Ian.
Between pandelas and lumens, is there a conversion?
I'm sure there is, and I don't know what it is.
Okay. What's the standard unit? Because it seems everything, at least, you know, you go to Home Depot, it's in lumens opposed to candelas.
Of course, we also use feet and inches in this country. So
Yeah.
I have a suspicion that lumens may not be a metric based. One of the places you could look, obviously, that you could look on the internet, but the Appendix A in the back of your lab book has an extensive conversion chart. You might want to look there.
Okay. Thank
So
you.
the ones that I expect you to pretty much know kind of off the bat are the ones that we use a lot of. So one big one, kilo. Kilo means 1,000. Then 4 little prefixes, deci, centi, milli, micro. So deci is a tenth, 0.1. Centi is 100, like there's 100 centimeters in a meter. Milli is 1,000, thousandth. And micro is a millionth. Things like bacteria are often measured in micrometers. So take a look at your textbook and your lab book for a few of the less common prefixes. You will run across nano and femto and pica and a couple of the other ones, and mega on the big end of things. You're going to use them just a little bit in doing your dimensional analysis lab, which is dry lab 1. So you will see them, the other alternate versions, just a little bit. All right, let's go back to units a little bit. And actually, I did not change this. This actually changed recently, the mass one, okay? Length has a definition based upon something that doesn't change. So light in a vacuum, okay? If you want to go and it's roughly 1/300 billionth of a second, 300 millionth, actually, 300 millionth of a second is a meter. Now, up until last year, there was in Sèvres, France, a platinum iridium cylinder in a vault, locked up, that was considered to be the absolute perfect 1 kilogram. Okay. Recently, they constructed I'll call it an equation that allows them to define the equation in a way that gives them 1 kilogram. Of course, the benefit to that is that other bureaus of weights and measures, like of course we do have one in the US, is not dependent upon comparing it to the original. So there's a benefit to that. Time is obviously 1/60th of a minute, but it's also based upon the decay of cesium-133. So there is a cesium clock on the Greenwich timeline in England. I have been there. I have stood on the Greenwich timeline. There's also a cesium clock, I believe, at the Naval Academy in Annapolis. And I believe that there is another one somewhere in Colorado. I don't remember exactly where. And because cesium-133 has a very, very specific radiation decay pattern, it can be used to define time. So one of the things we've been kind of skipping around is volume. Okay, that's one we didn't talk about. Because volume is a compound unit. It is based on lengths. So everything in metric is liters, okay? But a liter is actually 10 centimeters by 10 centimeters by 10 centimeters. So that gives you 1,000 cubic centimeters. And since 1 milliliter is a cubic centimeter, you can go back and forth. Again, this is something you should be comfortable doing. So 1.23 liters, you're essentially multiplying by 1,000 to turn it into milliliters. We get 1,230 milliliters. If you're going back in the other direction, you have 465 milliliters. You want to go to liters. This time you are dividing by 1,000. So 0.465 liters. So when you're doing measurements, and again, this kind of harks back to lab again, make sure that you are keeping track of the units that you are using, because some of the labs that we do might have you measure something in grams, but then in order to report your data or in order to do a calculation, you might have to change it to kilograms. Sometimes you have to convert back and forth between liters and milliliters. So make sure that you have some comfort in going back and forth between these different units. So switching topics again. Accuracy and precision. Media problems. If you listen to ads, often, unfortunately, there are a lot of ads who sort of mush together and inaccurately use accuracy and precision. So accuracy tells you how right you are. So I at various points in my life have been a fencer. I fence foil and epee. And if I am fencing against my opponent, if I'm fencing foil, I am allowed to hit my opponent anywhere on their vest, which does not include the sleeves, does not include the mask, and does not include the legs. So if I hit them once on the shoulder, once in the belly, and once in the side, I'm accurate, I get points, but my precision is awful. Because if I hit them 3 entirely different places, repeatability isn't happening, okay? Precision is the ability to do things more than one time. Some of the labs that we do this semester, a few of the real ones, and then also some of the digital ones, you'll be given data that is sort of real world data. It's not completely precise. There's a little bit of variability to it because sometimes you can get close several times, but maybe not exact. So you average to help compensate. I mean, in a perfect situation, you have both. So if I'm fencing against my opponent and I hit him on the arm 3 times, okay, my precision's great, but I didn't score any points, so my accuracy sucks. On the other hand, if I hit him in the side, because since when you fence, you sort of face somebody side on. If I hit him in the side 3 times, I've got accuracy and precision. So having both is what you are shooting for. Now we get into the dreaded sig figs. I probably spend less, we'll call it effort, less focus on this particular topic after we get past this chapter. Yes, this is a focus for this particular chapter. It will come up again a few times later in the semester, but the main focus is sort of this chapter. Significant figures are all the numbers you are sure of. And the first one you think you're sure of. We're going to call it the uncertain digit. Uncertainty is usually considered to be plus or minus 1 of whatever the smallest thing is. So I gave you a battery as kind of a an example there. So take your big D cell, okay, sit it on your balance. One of your balances maybe only reads to the nearest gram, and it tells you it's 61 grams. The balances we have in lab read to 3 decimal places. I gave you an example that had 2 decimal places. So the 6, the 1, and the 2 are your certain digits. Your 3 is your uncertain digit. So, okay, having more digits is helpful. It gives you closer accuracy in terms of what you are comparing. So when we do calculations, there are rules that apply here. Now, some of these are for the number itself. Some of them then get applied a further step for calculation. So here are the general rules. If it's not a 0, it's significant. But zeros come in 3 types. The first ones we're going to call the leading zeros. They're all the ones out in front that just kind of hold up space. Basically, you could rewrite that number in scientific notation and get rid of all of those zeros. The 0.00014, you could write as 1.4 times 10 to the negative 3rd. Only the 1 and the 4 are sig figs. Captive zeros, the ones that are trapped between 2 other digits, those are always sig figs. So 1073. The zeros in the middle, it's between the thousandths place and the tens place, so we have sort of 4 sig figs. The trailing zeros are a little vaguer because part of it relies on whether or not there's a decimal place. So if the hurricane happened down in Texas and Louisiana last night. So if I say 4,500 trees got knocked down, okay, the fact that I'm saying 4,500 is probably not an actual down to the nearest tree deal. So it's more of an estimate. I don't have a decimal place, and I'm only going to know for sure that the 4 and the 5 are sig. But when I look at my next number, okay, so if I have a beaker, a big beaker that weighs 210.0 grams, now I've got a decimal place. And whatever balance I weighed in told me the value down to the tenths place because it has a decimal point. It's going to have 4 sig figs. Now, the last one, in some ways, you could almost consider this to be kind of like a trick. In fact, if you look at examples at the end of the chapter, a lot of times they will do this for one of their examples. You have a number that has zeros in it, and then you put the point at the end, and which usually leaves people scratching their head for a moment going, is it a period? Or is it supposed to be a point? In this case, it's supposed to be a point. I weighed or measured whatever this was to the nearest ones, but it didn't have anything after the decimal place. So there are 5 sig figs because there is a decimal point. Now, for instance, if we were over at campus, okay, and you were counting cars in the parking deck over at MacArthur, and you said that there were 1,020 cars. Well, you can't have half car. Okay. Things that you can physically count are exact numbers. Therefore, you could say, yeah, there are 4 sig figs because I counted them, and that was the whole deal. Tamara, did you have a?
Yeah, I have a question. So you're saying like anything that has a decimal point, like all the zeros,
and then there's a decimal point at the end, then you actually count the zeros. It's a rare situation. It does not happen that often. Usually the textbook will give you a homework problem to look at, that they do that to you. They'll often give you an example that does it for you once. It's actually not something that happens a lot. Usually we're either have something like the 210.0 where you see the decimal point, or you just assume it's not there. Okay, the actually seeing the decimal point is not common.
Okay.
So irrational numbers, things like pi and e, square root of 1, irrational numbers also don't have sig figs per se. Like if somebody tells you to calculate the area of a circle and you use pi, well, obviously pi is infinite. Usually you're just using the number of sig figs that were in the radius, and not actually using the ones that are in pi, because you'd have a never-ending number of sig figs. Conversion factors work this way too. If I tell you that 1 kilogram is 2.2 pounds, the fact that it's a definition means if you use it in a problem, doesn't affect your answer. So now we need to apply the sig figs rules. There's some rounding. We're going to use the same standard batch of rules that math classes tend to use. If the number in front is 0 to 4, round down. 5 to 9, round up. And I wanted to give you an example. So if we have 34,879, round it to the nearest 100. So I look at the 8, because that's in the hundreds place. And then I look at the number that came afterward. Well, it's a 7. So I'm going to round up. Don't forget to put zeros in where you remove digits. If I said round 34,879 to the nearest 100, you can't tell me just 349. You could write it in scientific notation. You could write it as 3.49 times 10 to the fourth. But you can't just totally randomly delete the zeros. That's a common mistake when people are kind of working on through problems, is sometimes that they will forget to add zeros where they took digits away for rounding. So for calculations, there are two rules. For testing purposes and for homework purposes, I don't usually combine the two rules. You might end up needing to combine the two rules for math calculations in lab. The first one involves multiplying and dividing. So if I take 18.6, so 3 sig figs, and I divide it by 2.1987, that's 5 sig figs. So I put the number in my calculator. My calculator gives me, I think I had 8 or 9 decimal places on my calculator there. My calculator says 8.459544276. Okay, that might be mathematically correct. It's not really correct from the sig figs point of view. So using the smallest number of sig figs from the provided numbers. So I'm looking at the 18.6 and I'm looking at the 2.1987 number. I want to round it to just 3 sig figs. I'm going to round up. I'm going to round it to 8.46. When you're doing adding and subtracting, the rule's a little different. It's not least number of sig figs. It's least number of decimal places. So 5.95, 2 decimal places. 4.263, that's 3 decimal places. Again, do your calculator answer first. 10.213. But I only get to give my final answer, sounds like a game show thing, with 2 decimal places. This one I'm going to round down because my number dangling off on the end was a 3, so 10.21. There are 2 different rules. Like I said, for testing purposes and for homework purposes, I did not mix and match the rules. But for lab stuff, it might occur. Usually the rule of thumb for lab is dependent upon what your data started with and how many calculations you had to do. We'll talk about that a little bit more when we actually do the physical lab for density and other things. So one last topic I want to kind of deal with a little bit tonight, and we won't get to the end of the chapter tonight. We'll end up finishing the chapter on Tuesday. So this one's called, okay, some of the textbooks love to call it the factor label method. Some of them like to call it dimensional analysis. You'll also see a lot of textbooks just call it conversions. Yeah, my family is doing weird things in the background. If you're doing conversions, one of the things that you have to deal with is looking up the information that allows you to do the conversion. Okay, these are sometimes known as equivalent statements. There's a whole page of these in the back of your lab book, Appendix A. Like I said, you're going to kind of use this for doing dry lab 1. 1 meter is 1.094 yards, or 1 kilogram is 2.205. So starting with your equivalents and then looking at your problem, part of what you're figuring out is, what am I putting on the top and what am I putting on the bottom? So I gave you a couple of examples here. So stick of butter, 0.25 pounds, because there's four sticks in a pound when you buy them at the grocery store. You want to know how many grams that is? So I start with my information, 453.6 grams per pound. But I could write it two different ways. I could write it with the grams on the top, or I could write it with the pound on the top. The rule of thumb, and this is actually a math rule, not a chemistry rule, is put the one you want to find on the top, because that way the one on the bottom will cancel out. So if I have a quarter of a pound, 0.25 pounds, I'm going to multiply by 453.6. And since pounds is written over one when you're talking about math, pounds on the top and pounds on the bottom cancel out. I end up with 113.4 grams. So what if you're dividing instead? And I picked on a money conversion here. So money in Britain is pounds, okay, different kind of pounds. 1 pound sterling. And actually the current exchange rate is actually better than this. But I picked 1.63. So if I had 20 pounds and I wanted to know how much that was, $20, and I wanted to know how much that was in British pounds. Well, I want my dollars to cancel out. So my dollar sign and its accompanying number, 1.63, goes on the bottom. You are dividing the 20 by the 1.63, and you get 12 pounds and 27 pence is the way it's actually stated at the end of your conversion, because the dollars cancel out. So one last conversion here, and then we'll do some other stuff on Tuesday. Sometimes you need to line stuff up. Some of the high school classes tend to refer to this as the boxcar method, because you're linking several conversion factors in a row. It's also a common habit in physics classes. So, you know, the cinnamon rolls that come in the can, you know, you pop them open and throw them in the, yeah, of course my phone would ring. Throw them in the oven. If you read the information on the back of the can, it'll tell you that it's 230 kilocalories. Well, the British, or not the British version, the SI version is kilojoules. So I need to know the equivalence between joules and calories. So 1 joule is 0.23901 calories. So I set it all up together. I did calories and kilocalories. So there's kilo means 1,000 no matter what you're using. So 1,000 calories per kilocalorie. Then my second conversion factor was the joules and the calorie conversion. But I want to get all the way to kilojoules. So I still have to go back one more step. So 1 kilojoule is 1,000 joules. Your 1,000 on the top and your 1,000 on the bottom cancel out. Your 0.23901 is on the bottom. So you are essentially dividing 230 by 0.23901. You should get 962.3 kilojoules. So some of the conversions that we do are a single step. Some of the conversions that we do are multiple steps. Keep an eye on your units. What did you start with? What do you want to end up with? All right, so this is basically the end of class. This is roughly 2/3 of chapter 1. I will tell you for sure on Tuesday, but it is probable that chapter 1 homework will be due next Thursday. So since we've covered roughly 2/3 of the chapter, you may want to go ahead and download the chapter 1 homework and at least start working on some of it, the front of the page, over the weekend, so that you don't get too far behind in terms of the fact that we still have some things left to cover on Tuesday. Questions?
I have a question.
Yes.
So, okay, can you explain the butter dimensional analysis? I got kind of lost.
So everything is going to give you, or everything starts with whatever they told you.
Yeah.
So like in my examples here, I started with, a quarter of a pound, or I started with $20, or I started with 230 kilocalories. You always need a conversion factor. It's a something equals something, which can be written two different ways. And the way you figure out what goes on the top and what goes on the bottom is by asking that question of, oh, what am I trying to find? Find goes on the top.
So in that one, you're trying to find out grams.
Yes, yeah. For the butter one there, if I scroll back up just a little bit, for the butter one, I'm trying to find grams.
Yeah.
So I put the grams on the top of the conversion factor, 453.6. And I put the pound on the bottom because it's the one that needs to get canceled out.
Okay.
And I don't have a really easy way. I experimented with the whole what they call like the strikeout function of Microsoft Word. I experimented with that for one of the homework set answer keys that I'm working on. Makes it kind of hard to read, so I didn't do it when I did the notes here. If you go back and look in the textbook, there are some additional examples in the textbook to go with this part of the chapter that will give you some extra examples, and they will kind of show you with the little hash marks that goes, oh, this cancels out with this, and you may find that helpful.
Because I was trying to figure out like how you canceled out like the 1 pound. Like you just like what do you cancel?
Because okay, I don't know if you can see my cursor here.
Yeah, I can.
So if I look at the 0.25, it has in reality it has a bar, okay, and there's a one on the bottom. So like when you're doing fractions, if somebody says I have a 5 is 5 over 1. So in this case, I have 0.25 pounds over 1. So there is actually a bottom to the fraction, even though you don't see it. And then the pounds is on the top for the 0.25, and it's on the bottom for the other one. So as long as you have one on the top and one on the bottom, they go away. Because if you have them matching, one on the top and one on the bottom, they have to match. Then you get to cancel them out.
So if you're at the end and you're just multiplying the 0.25 pounds times the
453.6.
But then how come you need the 1 on the bottom anyways? Like, can't you just get rid of like the 1 pound on the bottom of grams?
It goes away, but what you're doing is you're making sure that you have your conversion factor set up correctly. Because if I multiplied by 1 over 453.6, I get a teeny tiny number, which is wrong. Okay, I'd get like 0.03 or something like that, which is too small. Okay, and also it wouldn't cancel out correctly. I'd have pounds and pounds over grams, and nothing would cancel.
Okay.
Gotta make them cancel.
Are we expected to memorize the conversions?
No. The only ones that I think you should be really, really, really familiar with were those 5 prefixes. For homework, obviously you can Google it. You can use the appendix in your book. But for test questions, I'm going to put it in the problem. Okay. Just like I put at the top of the butter problem, I said 453.6 grams equals 1 pound. I'm going to give you the conversion for things that are not those standard 5 prefixes.
Okay.
Oh, so the thing that you give us is what we put on. Oh, okay, is what we put on the bottom.
What I give you is the starting point. It's like the left-hand one. That's your starting point.
So that's what we're trying to cancel out is the thing that you give us.
Yes.
Okay.
Always.
I get it now.
I got a question about lab. So you split us. I kind of missed the point over there. We have two groups, right? A and B.
Yes.
So the next Monday, group A is going to the lab, right?
Let me grab my
Yeah.
reach over here and grab my pages. I did something with them. So people who are in group A
Okay.
will come to campus on Monday
Okay.
to the lab, room 1414 in the Andrews building. And we'll do experiment 1 plus 1 additional page that goes with dry lab 1 because it's the physical part of it. The people who are in group B will come to campus, not on the 7th because the 7th is Labor Day, will come to campus on the 14th of September, so 2 weeks later, and
So
do the same lab.
what group B does on next Monday? Nothing?
Oh no, log on to the lab section of Canvas. There are instructions. There's a whole module. Let me see if I can share this from Canvas. Hang on. It's gonna make me log in. Okay, so all right, so this is what the lab section on Canvas looks like. So it says dry lab 1. So I loaded instructions.
Okay.
Dry lab 1 is in your lab book. There's a video about burette usage because that's actually what you're going to be doing in lab. There's extra dimensional analysis examples. And then if I pop this open, this tells you kind of step by step how to go through the dry lab in your lab book, and it gives you tips. A lot of it is questions and math. So like part A is a lab check-in thing. You can just ignore that. For part B.
I'm from group B. So
Okay.
on Monday, we do all this stuff, but just kind of remotely.
Do you do it at home? Because it's just a
and then
paper, it's a paper lab.
Monday, but we do the same lab what we did at home?
No. Okay. So group A people will come to campus on Monday and do experiment 1. Experiment 1 and dry lab 1 are not the same thing.
Oh, okay.
Group B, sometime next week, it doesn't even really matter if you do it on Monday or not. Sometime next week, sit down and do the report sheet pages for dry lab 1.
All right.
Let me do.
Can I hop on Canvas?
So like, here's your lab book.
Here with
Okay.
that.
So there's a double numbering system here, which is weird. I didn't invent it this way. So this says dry lab 1. Okay. This is just a bunch of true, false, and questions, and short answer, and math. Okay. So it starts on, it says page 43, but it also says 51 in teeny tiny numbers at the bottom. I usually talk about the big numbers. So you're going to do that. And then there's 2 pages that are kind of info.
Okay.
Okay. And then there is no pre-lab for dry lab 1. That's what the quiz thing functions as. So then it says report sheet. So I've got a blank up here that I'm just going to leave blank. And this is part B, which is all just true false stuff. There's 3 short answer at the bottom. On the next page, there are some more short answer true false stuff. There's a couple of 1-step conversions at the bottom here. But then the remaining 2 do-at-home pages are problems. There's a problem about basketballs. There's a problem about a storm. There's a problem about a beaker. You need Appendix A to do these. Then there's another page that has something about railroad tracks and about heating up coffee in a cup, about aspirin. And then there's a picture at the bottom of a concrete piling. There's some tips on where to start to do these problems. This one last page here, this one that says extra exercises, Group A will do in the lab on this Monday. Group B will do in the lab on the 14th. Nobody is turning either dry lab 1 or experiment 1 in until the week of the 21st.
Okay.
So hang on to your stuff until you come back to lab for the second time, face to face, and you'll give me 2 lab reports because there's a 2-week cycle. I know that's weird. It's like the best we can do. Every 2 weeks, you will turn in 2 lab reports. That way, it gives chance for everybody to do the A group and the B group.
Does this
So every time we come to lab physically in person, we'll turn in our dry lab and our experiment
Yes.
lab.
Yes.
So technically, each lab has a 2-week turnaround,
Yes.
correct? Because we're going to be alternating. So until we've both completed that 2-week period, then it's due the following week. Is that
Yes.
accurate?
Yes.
Okay.
And
And that's going to be the same.
I have
all
some
future
due dates that I wrote into Canvas, but I'm still working out whether or not those are the actual valid dates. But yeah, it's like an every 2-week thing, which then doesn't quite, once we get really close to Thanksgiving, I haven't entirely figured out what to do about the whole Thanksgiving thing about the last 2 labs you might have to scan. I'm not sure about that yet.
does this pertain to only students that are in your lab course, or is it?
No, everybody in chemistry on the Norfolk campus
Okay.
is doing the 2-week rotation.
Well, I know that, but I'm saying as far as the dry lab, is it going to be exactly that same?
Yes, I believe so. I think everybody is using,
Okay.
well, okay.
Rick.
It's yes and no, okay? People who have lab Tuesday through Friday are not impacted by Labor Day. So they will end up 1 week out of sync with my Monday lab. But you are still doing 1 dry, then 1 real, then 1 dry, then 1 real.
Okay. As far as the lab manual goes, I contacted Barnes and Noble first thing Wednesday after we received the criteria for the book.
Uh-huh.
They have like a 3 to 5 day just processing time.
I posted as an announcement. Are you in my lab section?
No, I'm in Mr. McHugh.
Okay. I'm wondering.
If you go in person, they'll pull it for you.
I was gonna say there is a digital version. There is a digital version supposedly of the lab book. For my people, I posted it as an announcement. And hang on, let me see if I can scroll back up here for my screen share. All right. If you want to write it down, because I don't know if you can cut paste from your screen. This is supposedly the website that allows you to get the digital version.
Okay.
So standard HTTP, ::::. So store.vitalsource, appears to all be one word, .com/show/978-111-938-7510. This link was sent to me by Mr. Wheaton, so I have not had a chance. That's why I said I'm not 100% sure about this. I have not had a chance to verify that this is in fact the right link, but you can try it.
All right. Thank you.
If you have Mr. McHugh or Dr. McHugh, hopefully he got the same information. Has he activated his Canvas shell for lab yet?
Yes, but we weren't really sure on the direction. He mentioned the face-to-face and then the auxiliary assignment. We just didn't have any specifications quite yet.
Okay, because we have a syllabus, the syllabus that tells you about the rotation. And I think everybody in the department is using the same syllabus for that, the schedule.
Okay.
Because for one thing, everybody does the same 12 labs. Okay, we're going to do 6 real labs and 6 digital labs. And as after Labor Day happens, we are my Monday people are the last day of the lab week, and the first day of the lab week is Tuesday after Labor Day, which is sucky, but that's kind of what we ended up being stuck with. Hopefully, that's helpful.
Did you update the A/B day thing on Canvas? Because I registered today.
Yes, I did that this morning.
Okay, I'll have to look.
Because I had 1 drop and 1 add. I think you were my add, but I think I had a drop. So I have 20 people who are registered for my Monday lab section, and it should be like, I think I did it 10 people in group A and 10 people in group B.
Okay.
So yeah, I did update that. Other questions? I know this is hard. At least I'll get to see some of you face-to-face on Monday, and some of you face-to-face the following couple weeks, and a few of you I probably may not see face-to-face at all. Send me email if you have questions. That's the best I can do right at the moment.
And just to confirm for lab, again, sorry. So our lab, I'm in group B, what we do on the...
So next week...
next week we do dry lab.
Yeah, next week, read all the instructions.
Yes.
And then
Except for the last page.
Do everything but the last page that says extra exercises, and hang on to your stuff in your book. I would say don't rip the pages out. Hang on to it until you come to lab 2 weeks later to do the real physical part.
Okay, so is our dry lab being turned into on the 14th?
No.
Okay.
I think, I put 21st as the due date, but that actually doesn't.
We won't see you again until the 20th.
Yeah, I won't see you. So that's actually, I'm going to leave it listed, but that actually only applies to the Monday people. All the other people is going to be, they're in group B, is going to be a week later. And I can't put in 2 different due dates. Okay. Canvas won't let me do two different due dates. Okay. I'll figure it out when I enter the grades, but it won't let me do it the other way.
Okay, and all of our lab stuff will be turned in physically, not electronically. So all of our deliverables are going to be handed in, and maybe at the end of the semester.
That's not entirely true either. Dry Lab 2 has a Microsoft Word document that can be submitted digitally.
Okay.
For both the pre-lab and the lab report. If you get the digital version of the lab book, you could turn it in to me if you can figure out a way to save the page as a file. I actually don't know how that works.
I have other
Otherwise,
docs.
I am expecting people to actually turn in physical labs all the way up until the week before for Thanksgiving. The last lab or two of the semester is probably going to have to be digital because we will not see anybody face to face after Thanksgiving.
Okay. At which point we could scan them and send them over.
Yeah.
Is that accurate?
Yeah. I know that most cell phones will allow you to convert. If you take a picture of it, you can say convert to PDF, and then you can attach it and email it,
Okay.
or you can scan it. Either way.
Okay. Thank you.
I know this is complicated. It's not supposed to be this complicated, but unfortunately it is.
Assuming there's some kind of learning curve until all the dust settles, because I'm trying to keep up and it just seems a little crazy.
So for lecture, we are 2/3 of the way through chapter 1. We'll finish chapter 1, I presume, on Tuesday, which will make homework for chapter 1 due on Thursday. Hopefully that's a little helpful there. Some people who have me for lab, I will see half of you on this Monday. The other half of the people are doing the dry lab sometime that week. Doesn't matter when you do it. If it's a dry lab, it's up to you.
Not to further muddy the questioning, but all of the actual lecture homeworks will be turned in digitally.
Yes.
Okay.
You should
It's
save
just
them.
the lab stuff.
Yeah, the lab stuff is actually physical sheets of paper for the most part, not entirely, but a lot. Homework, download the Microsoft Word file. You can print it. You don't have to print it. That's up to you. You can do your work on a sheet of notebook paper and then type it in if you want. Save it as a doc, a docx, or a PDF. And then when you log back into the Canvas system, it'll say submit file. And it'll ask you which file do you want to attach.
Cool. Thank you.
Hopefully that works. Do I have questions from Kyle?
No, I figured it out.
Okay.
I got a non-homework question.
Okay.
This be simple for you. I hope you help me out. I never been to the Norfolk campus. Where do you park?
Where do you park?
I don't want to get told or anything like that.
So here are your options. If you're only going to be, since this is lab only and not lecture, my kind of advice is park at MacArthur Mall. The other options are the Freemason garage, which you enter right where like Freemason crosses Granby. It's like right on the corner. You can park there.
Okay.
You're gonna have to pay, okay? No matter where you park in Norfolk, you're gonna have to pay.
Right.
In some ways, the mall is the easiest. Freemason is the closest, but it's also more expensive. There is also the Bank Street garage, and up until now, students could go to the business office and buy a punch card. I don't know if they're doing that this semester or not, because only science students are actually having face-to-face labs. None of the lecture people are. So I don't know if they're doing the punch card system or not. Yeah, somebody said if you could find street parking, it's 35 minutes for 15 minutes up until 6 p.m. Yeah, but finding parking on Granby Street is tough.
Yeah.
So if you do park at the mall, where you go to get to like the building? I've never been to Norfolk one either. So like,
So
walk to like the.
if you come out, I'll call it the front of MacArthur, where the Texas de Brazil is. Okay, you walk across the street, past. Basically, you can see the Norva when you come out the entrance there. The Norva is just off to your right a little bit. Go across the street 1 block forward. That'll put you on Granby Street. Turn right. Go half a block essentially. And the Science building is on the opposite side of the street there. It's across from the student center, which has this weird wavy, like, profile on the front of it. It like has like a curve to the glass. And we're up on the 4th floor.
Does
So you
it
have to
say
come in.
building on top of the building? Like how do I?
The wavy thing is actually kind of the front of the building. I mean, it like,
If you have a smartphone, just put it in Google Maps from the parking lot and put it in walking, and it'll take you right to the front of the door.
yeah, it's 2 blocks from the mall. Not even fully 2 blocks. If you go out the front of the mall.
Okay.
I park at the north end of the mall. I park in the part of the garage that faces the big green grassy spot. And I walk out of the garage past the Cajun seafood place, down the side of the block over to Granby and hang a right, or hang a left actually. And then I walk 1 block down because I go the other way. I go the other direction. It's pretty straightforward. We start at 5:30. So if you don't have work issues transportation wise, the first time around, you might want to give yourself an extra 20 minutes.
Yeah, I will do that.
I work for Hampton Road Sanitation. We got a pumping station off of King Street. I might just park there and lock my car up. It's right in front of the mall. So I might.
Yeah. Yeah.
I don't know. I have to see how far I have to walk. I don't mind walking, but I don't want to be late either.
Yeah.
So,
Or if it rains or something.
that's what I'm saying. You can get.
Yeah, I don't know.
So okay, that was good. That I didn't know exactly where there any parking nearby. I thought about catching a train, but I don't know.
The problem with the train is it takes so long from point A to point B.
Mhm.
And yeah, it drops you off pretty close, but then you're dependent upon the train schedule.
Yeah.
The trains come every 15 minutes, and it will take you up somewhere between 15 and 20 minutes to get from, say, the Newtown Road stop, which is where I used to go,
Yeah.
to the MacArthur stop.
They arrive every 15 minutes, but it takes about 20 minutes if you're coming all the way from Newtown Road.
Yeah, I ride right past Newtown Road. I get off at 3:30, so I'm like, I ride right past the Newtown
You could.
Road.
It's a toss-up. Either you're paying the fee for the tide or you're paying the fee to park.
Yeah.
It's going to cost you a little bit, kind of either way.
Yeah.
All right. Appreciate it.
All right. So I will see some of you on Monday. Send me email if you're stuck on like what to do about lab or whatever.
All right. Thank you.
Bye.
Bye-bye.
Weekend. Bye.
Bye. Thank you.
I